When choosing wire for any particular project, the diameter of the wire makes a difference. You have to be careful because if you choose wire that's too thin for the amount of current that you need to pass through the wire could get hot and start a fire. The thickness of a wire, the diameter of a wire, is characterized by the wire gauge. I have some spools of wire next to me here of different gauges. This is thicker wire and this is thinner wire. Wire gauge has an inverse relationship to the diameter of the wire. So this thicker wire here actually has a lower wire gauge than the thinner wire over here. I'll show you in a moment what this relationship is. I also have a cable up here. I'm calling it a cable rather than a wire because it actually has 3 wires inside. This is 13 amp wiring, and it says on the side 13 amps made in Italy. It follows the European standard for the color code here. We have brown wire, a blue wire, and a striped green and yellow wire. The brown wire is for hot, the blue wire is for neutral, and then the striped green and yellow wire is for ground. If a wire can carry more current, then it's going to have to be thicker than a wire that doesn't carry as much current. Other than the thickness of the wire, what are all the considerations that one needs to consider when choosing a wire for a particular project? Let's talk about all of them. Of course, as I mentioned, the amount of current that a wire can carry makes the most difference. You might recall the formula for resistance as being rho times L divided by A. Rho is the resistivity, so it's a property of the material used in the wire. In the case right here on the desk, it's copper, so rho would be fixed. But then the length matters and the surface area matters. So the cross-sectional area is what we're concerned about here. If the cross-sectional area is larger, then the resistance of the wire is going to go down. That means the wire is not going to get as hot because it's not going to be burning up as much power. Of course, the metal used in the wire also matters. Whether it's copper or aluminum, for example, makes a difference because that influences the resistivity rho in this equation. If you use a material with a very low resistivity, then the resistance per unit length is also going to be lower. Silver, for example, has a very low resistivity, but silver is very expensive relative to copper. Because this equation also contains L, the length of the wire, the length of the conductor, the distance over which you're going to transmit the power also makes a difference. There's always going to be a voltage drop across a wire because a long wire behaves a lot like a resistor. So if you have, for example, too much of a voltage drop across a length of wire, you can always use a thicker wire to counteract that voltage drop. The flexibility of a wire or the flexibility of a cable also matters. If you're finding yourself using a very thick wire and it's hard to bend the wire around corners, then you might choose a stranded wire. That is, a wire with multiple wires inside of it all bundled together. The voltage of the signal or the voltage of the electricity passing through the cable also matters because that influences the amount of insulation one needs to place around the copper or around the aluminum. If a wire is going to be operating at a low voltage, then you need less insulation than you would if the wire is going to be operating at a higher voltage where somebody might touch it. The frequency of the signal passing through the wire also matters, and I'll get into this a little bit later in this video. But suffice it to say that at low frequencies, the equation that I have up here for resistance is accurate. But as the frequency gets higher and higher, then the effective resistance or the attenuation in the wire starts to increase. And that's related to the fact that as the frequency gets higher and higher, the current is not passing uniformly through a particular cross-section of a wire. The color of the wire also matters too. You need to follow certain standards to make sure that anybody who encounters your wire, say in a building, would know which color corresponds to, for example, whether or not that's a current-carrying cable that's hot, or whether it's a current-carrying cable that's neutral, or whether it's a safety cable, an earth ground, for example. Finally, the cost matters, and you might be familiar with the fact that overhead wires in a power distribution center are typically made out of aluminum rather than copper, and the reason for that is aluminum is cheaper than copper. Let's now talk about wire gauge. I mentioned that wire gauge has an inverse relationship to the actual diameter of a wire, meaning a smaller number on the wire gauge refers to the fact that a wire is thicker, not thinner. This formula shows you how to convert the wire gauge N into a diameter D. You can see that there's a minus sign in front of the N, and that's where this inverse relationship comes from. I'm giving the formula here for both inches and millimeters. I should also point out that these two formulas here refer to the American wire gauge, AWG. There's another kind of wire gauge called SWG, or standard wire gauge. That's British standard, and the numbers are not compatible. They still have an inverse relationship, and the numbers are usually only off by 2 or 3 gauges, but it's important to keep in mind that the two standards are different. Neither of them are in the metric system, but it is possible here to convert wire gauge to square millimeters in terms of the cross-section. Let's look at a couple of examples here. In the first example, let's find the resistance of 1 meter of 24 gauge copper wire, and we're assuming here the American standard. First, let's find the diameter of the wire. We'll use the formula for millimeters. I'm going to substitute in 24 for N since we've been told that this is 24 gauge wire. The formula tells us that this wire is about a ½ millimeter in diameter. Radius is half of the diameter, or 0.255 millimeters. The surface area of a cross-section of the wire is pi r squared. So if we substitute in for our radius, we find that this wire has a cross-sectional area of 0.205 square millimeters. We now have all the information we need in order to calculate the resistance of this wire. Plugging in the resistivity, the length, and the surface area, and then converting square millimeters to square meters, we find that the resistance here is 84.22 milliohms. Let's work another example with 21 gauge copper wire. We'll again use the formula above in order to find the diameter of the 21 gauge copper wire in millimeters. We can see immediately that the diameter of 21 gauge wire is larger than the diameter of 24 gauge copper wire. The radius is 0.362 millimeters. We can then find the surface area of a cross-section of a segment of this wire. It works out to 0.410 square millimeters, and you might notice that this is nearly double the surface area of the 24 gauge copper wire. We again have all the information we need in order to find the resistance of 1 meter of this wire. I want you to notice that the resistivity is almost half of what it was with the 24 gauge wire. And in fact, this turns out to be approximately true for all gauges. If you reduce the wire gauge by 3 units, you effectively double the conductivity of the wire. So that's a good rule of thumb that's worth remembering. Of course, the amount of current that a wire can handle is the most important consideration when choosing the diameter of the wire. The chart here shows the recommended maximum current that you can pass through wires, and there are a few considerations here to keep in mind. Let's look at the line for a 28 gauge wire as an example. First of all, if you get a wire hot enough, it's going to melt. The copper itself is going to melt down into a liquid. That would be very similar to the situation inside of a fuse, and you definitely don't want the wire to get that hot. But what temperature do you want the wire to actually get to before it melts? Obviously, you don't want it to get so hot that it could melt plastic inside your case or cause damage to other electrical components. If you look at the last column here, you can see what the melting current is if you have that much current passing through the wire after about 10 seconds. So what we can see here for 28 gauge wire is that if you have anything more than about 14 amps of current going through the wire will melt after about 10 seconds. But you don't want to have less than 14 amps of current going through it either. You don't want to say pass 13 amperes of current through the wire because it's still going to get really, really hot. The melting point of copper is nearly 1,000 degrees Celsius. So if you have, for example, 13 amps of current going through 28 gauge wire, the wire is going to get super, super hot. And when a wire gets really hot like that, it can do a lot of damage to other components inside your case. It can melt insulation, or it could even start fires. If, for example, you have a wooden enclosure, it's worth keeping in mind that wood can ignite at temperatures as low as 260 degrees Celsius. So if you have copper wiring nearby a wooden enclosure, and the copper wiring gets hotter than, say, 260 degrees Celsius, then you could have a very dangerous situation on your hands. The copper could start a fire before it would melt. So for that reason, we have here on the chart some recommended maximum values that are considered to be safe. For 28 gauge wire, if you pass 1.4 amperes of current through the wire, then we expect that that wire will stay below approximately 60 degrees Celsius, and that's considered to be safe. However, if your wiring is enclosed inside of a chassis where the air is trapped, where there's no fan, then the wiring can get hotter because it's hard for that heat to escape. The recommended maximum current inside of a chassis is around 0.8 amperes. So I hope you can get some idea here of how the chart can be used. You should know anytime you're designing a circuit or any kind of a power distribution system how much current you expect to flow through any particular segment of wire. This chart will then tell you what the recommended wiring gauge is to use. You'll notice here that as the wire gauge gets larger and larger, the wiring is actually getting smaller and smaller, and the maximum allowable currents, or the maximum recommended currents, are getting correspondingly smaller and smaller. There's one more thing I wanted to point out about wire gauge, and that's what happens when the wire gauge numbers get lower than 2, or when the wires start to get really large. The numbers go 2, then 1, and then 0, and then rather than stated in negative numbers, they start piling up zeros. So they have AWG 0, and then AWG 00, which is sometimes called aught or double aught wire. So if you see a lot of zeros as the wire gauge, that's super thick wire. The US National Electrical Code, by the way, has different recommendations than what we see in this chart, which I've gotten from various references. You might notice here that the recommended maximums from the US National Electrical Code are a little bit lower than the maximum currents from this other reference I have here. The reason for the difference is because they want to be really sure that a fire is not going to get started. In the US, a lot of houses are made out of wood, so you don't want the wiring to get very hot. You want to be super safe when you're using wires, especially inside of wooden structures. Also, when you're using wires in a power distribution system, the wires tend to be longer than they would in small projects, for example. The chart here was for copper, but I also wanted to show how these numbers change if you're using aluminum wires, and these are common for power distribution systems. The reason for that is because for any particular wire gauge, the resistivity for aluminum is going to be a little bit higher than the resistivity for copper. Let's look at a simple example here. A wire in a small electrical project needs to carry 600 milliamps. Should we use 28 gauge or 30 gauge copper wire? Well, let's look at the chart and make a design decision here. Since we've not specified whether or not this project is going to have the wires exposed to air, where you have good thermal conductivity, or whether or not it's going to be enclosed in a chassis, we want to be safe and we'll use the chassis number. We can see that 600 milliamps lies right in between the recommended maximum currents for 28 gauge and 30 gauge copper wire. So should we round up or should we round down? Well, we want to err on the side of safety. So given these two choices, we should choose the 28 gauge copper wire because it's thicker. It's not going to get as hot, therefore it's safer. Let's now work a more complicated example. Let's say that you're designing the wiring for an aircraft. An aircraft requires, say, 100 meters of 5 amp wiring. If the resistive loss needs to be less than 25 watts, then should we use aluminum or copper? The consideration here is that we're making an aircraft, so the weight of the wiring matters. Normally, you want to use something that's lightweight. Copper and aluminum have different resistivities though, so which one is going to make more of a difference? Should we use thinner copper wire because it's more conductive, or should we use thicker aluminum wire because it might not weigh as much? That's what we're going to determine here in this problem. Wires are typically cylindrical, so we're going to model the 100 meters of wiring as a very long cylinder. The cylinder is going to have length L and cross-sectional area A. This long section of wire is going to behave like a resistor, and we're told in the problem that it's going to dissipate 25 watts in the worst case scenario. The maximum current flowing through the wire would be 5 amperes, so we have enough information now to find the resistance of the wire. We know the formula for resistance. It's related to the resistivity, the length, and the cross-sectional area. We know the resistance, but we don't know the surface area, so let's rearrange this equation and find the surface area. You might notice here that my resistivity for copper is a little bit different than the resistivity I was using in one of the earlier examples. And the reason for the difference is because here I'm using the resistivity for annealed copper. I now have the cross-sectional area of my copper wire. What I need to do now is to find the mass of that copper wire. I know that mass is volume times density, and volume here is just my surface area times my length. Along with some unit conversions, I find that the mass of the copper wiring would be 1,548 grams. Let's find out what the mass of the wiring would be if I were to use aluminum instead. The resistance is still going to be 1 ohms, but the surface area is going to be different. It's an interesting trade-off here because aluminum is lighter, but it's also more resistive. There we have the volume, and the density was given in the problem. After converting cubic centimeters to cubic meters, we can determine the mass of the aluminum. Finally, we find that the aluminum wiring would weigh 715.5 grams, but the copper wiring weighed nearly 1.5 kilograms. Copper wiring is almost twice as heavy as the aluminum wiring, even though the diameter of the copper wiring is going to be smaller. We can conclude from this that we should choose aluminum as our wiring for the aircraft. There is one practical consideration, and I'd want to point this out. Aluminum is more difficult to solder to. Copper wiring is really easy to make solder joints to, but aluminum tends to be very difficult. So it's just something to keep in mind if you, for example, want to use aluminum wiring to make a drone. I mentioned earlier in this video that one also needs to consider the frequency of a signal passing through the wire. In all of the examples that I've considered till now, I've made the implicit assumption that when current passes through a wire, it roughly fills uniformly a particular cross-sectional area of the wire. That's really not the case as the frequency gets higher and higher. And I wanted to introduce you to a term called the skin effect, or the skin depth. It happens when you use alternating current, and it's an effect that becomes more pronounced the higher the frequency. What's shown here in red is the area of the wire where you have most of the current flowing. What you can see here is that most of the current flowing through a wire is concentrated out near the edge of the wire. The higher the frequency, the closer towards that edge, or the closer towards the skin, the current tends to congregate. What this means is that if you need a wire to handle more current and you're operating at a higher frequency, making the wire thicker will not necessarily help you very much because the interior portion of the wire doesn't carry any of the current. The current is occupied out near the edge. One needs to be very careful then using these charts for wire gauge that I showed earlier in the video. The charts become useless, or at least they need to be modified if you're not going to operate at very low frequencies. If you're operating at line frequencies like 50 or 60 hertz, then the charts are okay. If you're operating at DC, then current is going to flow uniformly through a given cross-sectional area. We're talking here about higher frequencies like kilohertz, megahertz, or gigahertz. In those situations, the current is really flowing only along the skin of the conductor. The skin depth can give you some idea of the maximum allowable diameter of a wire at a particular frequency. The skin depth is a function of the resistivity of the particular metal conductor, the operating frequency, and the relative magnetic permeability. For copper, the relative permeability is nearly 1. Let's look at some examples here. At a frequency of 50 hertz, the skin depth of copper is about 9.22 millimeters. That means that if you have a conductor with a diameter, say, more than about 20 millimeters, the center of that conductor is not going to carry very much of the current. For that reason, you'll almost never find power cables with thicknesses more than about 1/2 inch or a couple of centimeters. If you need a conductor that can handle more current than about 1/2 inch of diameter, then you can bundle them together. So it's very common in very high current carrying conductors to have bundles of wires rather than just a single conductor. You can see that if you operate at very, very high frequencies like 100 megahertz or a gigahertz, then most of the current is concentrated near the outer few microns of wire. For that reason, you could even, say, replace the interior of a wire with some other material. A piece of glass coated with a couple microns of silver might actually be a better conductor than a thick copper wire a few centimeters thick if you're operating it at a gigahertz, for example, because only the outermost skin is going to actually carry the current. I'm not going to go into too much detail about why physically the skin effect occurs, but suffice it to say, it only matters for AC circuits. Anytime you have alternating current, you're going to generate magnetic fields which change with respect to time. Whenever you have magnetic fields that change with respect to time, you're going to influence the current inside the conductor that carries the current. So you could say that, well, it's really because of the interaction of the magnetic field with the electrons inside of the cable. Again, it's only important for AC circuits, and I wanted you to be aware of it because you wouldn't want to use the charts, for example, in order to design a circuit and then be surprised when they won't work for AC. We have a whole series of professionally filmed and edited videos in order to help students learn the fundamentals of electricity. If you like watching this particular video, then you might like to check out some of our others too.